I can gain.
And we can use better the time.
Yeah. I can exploit also these 2 minutes more. So
Sure.
thank you very much for being here. Thank you very much for your attention. So today we'll discuss about the GPGPU methods to simulate the combustion problems with finite rate chemistry, of course, in CFD. Our say research in the exaFOAM project is related to the fact that we want to accelerate the solution of these kind of problems. Okay, so involving specifically finite rate chemistry. And before to start, I would just want to provide to you the agenda of this presentation. So this presentation will start from a brief introduction. Okay, I will just be quick on this because I expect everybody to be familiar with the topic. But if not, of course, I will cover what is necessary to understand what is going to follow. I will then move to the CFD treatment of the chemical of the system. What I mean by that is how specifically OpenFOAM handles the chemistry, finite rate chemistry in particular. And so what is the CFD treatment specifically related to the ordinary differential equations, which are addition of usual equations that you have because of the fluid dynamics. Then I will move to the description of how we can try to exploit heterogeneous supercomputing in order to treat these problems and to fasten up their solution. By heterogeneous supercomputing, I mean the use of different hardwares combined together. So usually I refer to that as a combination of CPU and GPUs. So CPUs are the common, say, processors that you use to develop your simulations, while GPUs are the graphics processing units, okay? And the GPGPU stands for the possibility to exploit the GPUs for different approaches with respect, or different, let's say, programming with respect to their common application, which is the graphics field. So we try to exploit the architecture of the GPU, and I will show you how and in which sense to fasten up the solution of these kind of problems. I will then move to the discussion about the numerical solvers that we can use combined with this, let's say, novel GPU integration method. Then I will show you some test cases that have already been validated. So this kind of approach I'm going to show you has already been tested on some simple cases, let's say, starting from single cell batch reactors. There is a reason for that, but I will explain it when we get there. And then moving to multi-cell cases, okay? Related to this, I will then discuss about some observations that we can already derive and some discussion about the performances that we currently have. And then I will go back to discuss a bit the macro benchmark, which we consider as, let's say, more complex test cases or industrial, in some sense, test cases that are currently under analysis and development in terms of, let's say, the solution of these test cases by means of the novel heterogeneous methodology. And so I will derive some general conclusions related to this. I will not stay too much on the discussion about the macro benchmark because, of course, you have already seen an extensive discussion of this provided by Flavio. So I will just move a bit quicker on that. What is interesting is related to the methodology. Then I also added a little extra, which is not directly, let's say, linked to the exaFOAM project, but it's still related to how we can exploit the use of the GPUs to fasten up the solution of a lot of problems which are currently handled in CFD by means of OpenFOAM. Okay, so let's start by stating why we want to tackle this kind of problems. So for all the people who are familiar with combustion problems in CFD or finite rate chemical problems in CFD, you know that whenever we handle this kind of situations, more than the fluid dynamic equations, we need to add a set of equations, and so the problem becomes more complex, more let's say expensive in terms of computational cost, and also becomes longer in terms of computational time to be solved. The reason is not only related to the fact that we are refining our mesh because we want to obtain, let's say, an accurate result, and in some sense to try to replicate as good as possible the reality when we can, but it's also related to the fact that we are shortening the, say, time advancement. So we are reducing usually the current number, and in combination with the high number of cells, and so the small dimension of the cells, we have very short time steps, so time advancement is very limited. But we also have an addition of some equations. I'm not only talking about the presence of convection diffusion equations because of the presence of the chemical species inside of the domain, but we also have to solve ordinary differential equations, which are connected to the complex, let's say, chemical chain that in finite-rate chemistry you have inside of your simulation. So whenever you handle this problem, of course, there have been in the literature and throughout the years some methodologies which allow you to fasten up the solution of these kind of problems by means of, for example, tabulation or reduction, some sort of accelerators. Some drawbacks that they have, even though they are very efficient, is the fact that you, in some cases, have to spend a lot of time in pre-processing because you need to construct some tables, or you need to construct, for example, if you use something which is quite recent, genetic algorithms, you need to generate, let's say, an extensive pre-processing before to actually launch your simulation. Or when you use reduction, in some sense, you are simplifying your problem because you are saying that a portion of your chain is not accounted, or let's say, it can not be accounted in some specific conditions. So you are simplifying a bit your problem by reducing the complexity of your chemical chain, so perhaps reducing the stiffness, which also influences the time step, and so the advancement of your simulation. So we want to find out a different way, okay, to accelerate these kind of simulations by using the hardware, which is nowadays usually used inside of supercomputers. So we want to exploit the use of GPUs to accelerate the simulation while preserving the same direct integration that you have whenever you don't produce, for example, reduction, or possibly combine this with reduction to fasten up even further the simulation, and avoiding the use of preprocessing or extensive preprocessing that, of course, might cost a lot for the industries to be done before the actual simulations. So just to move very quickly to the analysis related to the, let's say, governing equations that we have, which is something that I have already pretty much discussed. You not only have the presence of NS, let's say, -1 partial differential equations for the convection diffusion of the chemical species, which are the one at the top inside of the system. You have NS -1 because, of course, for the inert species, you consider that the sum of the mass fraction must be unitary. But you also have the fact that the heat, let's say, the source terms related to chemistry. So in the equation that you see at the top, you see the omega dot I bar, which is the reaction rate, let's say, adjusted because you have combustion models inside of the CFD framework. Okay, but not only that, also the Q dot, which is typically added as a heat source to the energy equation, need to be computed. Okay, starting from ordinary differential equations. And ordinary differential equations, so which can be, let's say, summed in the OpenFOAM framework by means of the last equation that you have, require the knowledge of the concentration at the end of the time step, which is something that you get once that you have done the ODE integration. Of course, the integration can be done by means of implicit methods, explicit methods, so explicit or implicit ODE integrators, but you need to have these kind of value. Okay, in order to get the reaction rate and so to determine the chemical sources. So these are the terms that we want to compute by means of the GPU. So we want to compute in particular the reaction rate or the update of the concentration so that we can move back this information to the CPU and then update this information, whether it is necessary, by means of the combustion model, and then add it to the equations. So add omega dot to the convection diffusion equation or add the Q dot in the energy equation. Okay, I want to start by saying that because of the fact that we use the GPU, and it will be clear in a moment in which sense we use the GPU, and so what is the methodology that we implemented. I want to start by saying that, as I said, you have two options, so implicit ODE integrators and explicit ODE integrators. But because of the architecture of the GPU, so because of the way the GPU works, we have found out that the use of explicit ODE integrators is advantaging because the GPU relies on the single instruction multiple thread approach, which, let's say, eases the implementation, but also enhances the speed up whenever you're using something which is explicit. Now, the way we have designed our approach that I'm about to present it's anyway possible to add other integrators. We just started by introducing the explicit integration of the ODE systems, because of course it's advantaging when you use the GPU, okay? So here we go to discuss about the way that we use in order to accelerate the simulations by means of the GPU, particularly referring to the finite-rate chemistry. So we have to keep, in some sense, separate the CFD solver, okay? So basically the solver that you have in OpenFOAM, which of course takes into account the presence of finite-rate chemistry, with respect to the GPU. So you know for a fact that whenever you launch your solver, your quantities are resident on the memory of the CPU. So, and the solver, whenever you consider the fluid dynamic equations, it relies on the solution of the PDEs, okay, it relies on the solution of the PDEs on the CPU. So we preserve the solution of the PDEs on the CPU, but when it's time to solve the ordinary differential equations, we need to rely on the GPU. So there are two connections that we have to make. The first is that the memory of the GPU needs to, in some sense, be connected to the memory of the CPU. So they need to share information. And we do that by means of NVIDIA libraries, because we rely on the fact that we are using NVIDIA GPU cards, and NVIDIA produces some libraries which facilitate to us the possibility to reduce the amount of coding and avoid any kind of memory spillage or leakage or any kind of issues. And so we rely on these kind of libraries to put in communication the memory of the CPU and the memory of the GPU. We only transfer the amount of data which is actually necessary for the solution of the ODEs. Then when it's actually the time to solve the ODEs, we need to call a kernel, so which is a global function, that is a function that is resident on the GPU. So it can actually work only on the GPU. The issue that we have here is that whenever you design a program or a software which works on the CPU, you cannot directly call a function on the GPU. You can't, because the compilation is different, and so it cannot accept the compilation of a function which it has to be called on the GPU. So we need to rely on a bridge. So we construct a bridge which is called the extern C, that when it's the actual time to solve the ODE, let's say equation, so the ordinary differential equation, it calls, so inside of the kernel, which is compiled via NVCC, which is a compilation for the GPU, it actually calls the global function, which is able then to solve the ODE equation. So it takes the information from the GPU memory, it solves the ODEs, and then it produces, so let's say, saves, it stores the information, so the output on the GPU, and then we have to transfer these output back to the CPU, and then use these output on the CPU to do the subsequent task, which are the common ones that are done by the solver that you have in OpenFOAM. So talking about how we, let's say, physically do this, you need to think about the fact that the fluid dynamic problem is solved on the CPU in the same way as it is solved now by relying on the MPI libraries. So you decompose your domain exactly as you do right now for the fluid dynamics. Then when it's the time to solve the ODEs, you need to transfer the data from the CPU to the GPU. And here, because of the fact that we are relying on the use of NVIDIA GPU cards, and the NVIDIA GPU cards are structured on the CUDA architecture, which is composed by 3 levels. So it has a hierarchy of 3 components. So the grid, the blocks, and the threads. We exploit this architecture by producing a 2-level parallelization for the GPU, okay? And so for the solution of the ODEs. So what you have right now is that the ODEs are solved in serial for every single cell on the CPU, and you have that every single chemical species inside of every single chemical cell is handled in serial in the CPU. So what instead we do is to exploit the architecture of the GPU to produce a double parallelization. What we do is we solve multiple cells concurrently on the on the GPU, okay, as CUDA blocks. And since in every single cell you have the presence of chemical species, you handle every single chemical species inside of each cell in parallel. And so you're producing a two-level parallelization, okay? By considering, of course, the threads. So the two-level parallelization is connected to the architecture of the GPU. Blocks, cells, and threads with species. So this allows us to have a massive parallelization. This kind of approach is called a fat thread approach, okay? And we need to rely on this with respect to the thin thread approach, because at some point throughout the solution of the ODEs, the different information related to the chemical species contained inside of the cell need to communicate one another. So there are some operations that need to have some kind of communication among the different species. So because of the fact that communication among the threads is lightweight, while it's not lightweight, it's even recommended not to have hard communication among the different blocks of the GPUs. We need to rely on the fat thread approach. So the fat thread approach needs, of course, or has some effects on the way we organize the data and we organize, let's say, the structure of our data. And of course, it has some effects on how we handle the memory. So the first thing that we decided to do is to also think about the kind of memory which is available in the GPU, so from the hardware point of view, and say, okay, we can allocate a certain amount of constant memory and access that in a coalesced manner so that we can fasten up the access to this kind of memory. And we can store in this chunk of memory, which is not that large, only the information which is constant throughout the simulation. There are a lot, of course. For example, the molecular weights, for example, all the, let's say, constants for the ODE method that you are going to use. For example, the indexing, stoichiometric coefficients for the chemical reactions that you have. All of these can be stored in the constant memory. They are allocated at the beginning only because you can understand that we are losing time whenever we're moving data from the CPU to the GPU and vice versa. So we want to avoid to copy data when that is not necessary. So then what we have is a large chunk of memory, which is the dynamic memory, okay? And we use the dynamic memory to actually store all the information which is constantly varying throughout the simulation for every single cell, okay? So we take this information, the temperature values, the pressure values, values of the mass fractions for all the species in every single cell, we move them on the GPU. And there, because of the structure that we have, we can actually perform this double parallelization, okay? There is another thing that we need to consider, which is the fact that whenever we use a fat thread approach and whenever we have to share information among the thread, it is quite fundamental to use another chunk of memory, which is called the shared memory in the GPU, which is not large, but is the fastest one. And why we use shared memory? Because this is the amount of memory that can actually communicate among the different threads. So what we do is we use this kind of memory to allow the different quantities, different threads to communicate. But the point is that the number of threads depends on the number of chemical spaces that you have. So the problem is that you cannot decide a priori what is the number or what is the amount of chunk of shared memory that you have to allocate. And that's why we designed shared memory to be dynamically allocated and be resized throughout the simulation, depending on the effective data that we need to share among the threads, okay? So it's dynamic in this sense. Then, of course, what we do is we perform, by means of this double parallelization, as I said, the solution of the ODEs. Now, the solution of the ODEs occurs explicitly, as I said, and it occurs by means of the Runge-Kutta-Kashkarp method, which is already available in OpenFOAM. So it is the same Runge-Kutta-Kashkarp method which is available in OpenFOAM. But of course, you cannot directly take the Runge-Kutta-Kashkarp 45 which is present in OpenFOAM and move it to the GPU and expect to have performance benefits. Because of course, that is designed to be, or the structure in OpenFOAM is designed to be serial. Okay, and so to handle the things in a serial manner. So we had to redesign the ODE integration in order to allow this kind of operation to actually occur. Okay, so from this perspective, what you have is that from a numerical point of view, so from an informatic, let's say, point of view, what happens is that whenever you get to the point where you need to solve the ODE equations, you have some libraries which allow you to allocate and copy the GPU memory, so allocate the GPU memory that is required, and copy the CPU data onto GPU, okay, directly. Because of the fact that we are using these libraries, we have the advantage, as I said, to avoid memory leakage. But at the same time, we also have another advantage, which is a huge reduction in the number of lines that we have to actually write. And we don't have troubles that might be encountered whenever we finish our job, because if we didn't use these kind of libraries, we had to manually free all the memory of the GPU. But we don't do that because we use libraries which do that automatically for us. So once the data is copied onto the GPU, we launch the kernel call, which is the, let's say, the green line that you see in the algorithm on the right, okay? And as you can see, you have this quite peculiar triple bracket call, okay, whose elements inside, usually whenever you see, for example, let's say, common codes which are also available online by using the GPU, you might have seen, for example, only two quantities introduced inside of the triple brackets. And they are typically related to the grid decomposition that you use, okay? Instead, we need to rely on a third element, which is introduced inside of the triple brackets call, because we need to dynamically allocate a certain amount of shared memory, which otherwise would be directly called and directly allocated inside of the kernel call, and you will not have this kind of element inside of these triple brackets call. Once the operation is concluded, the only thing that we need are the actual reaction rates and the, let's say, the guess on the time advancement for the next iteration, so for the next fluid dynamic iteration. So we only take these two information, we don't care about the rest. We only take these two information, we move it back, okay? So we reduce the amount of time which is passed because of data copy backwards, and we provide this information in the same format as the standard OpenFOAM, so that OpenFOAM can use it to proceed with the rest of the calculations. Okay, and as I said, then the memory is automatically deallocated. Okay, so about the, let's say, implementation, I've pretty much already said everything. The only thing that I didn't say, but it's worth mentioning, is the fact that we had to design all the code, so we had to modify all the code to be branchless. The reason is that, again, because of the way the architecture of the GPU is designed, you cannot have branching inside of the GPU. I mean, you can, but you shouldn't, because of course, whenever you have some kind of branching, the issue is that you have serialization of your operations. So the operation gets serialized, and then of course you lose all your performance benefits. So the code has to be written in branchless form. Let's say the minor issue that you might get is the code is lower. The larger issue that you might get, the result is totally incorrect because some threads has been stuck in some place and so has not produced the correct result because you had thread divergence. Okay, so you need to avoid that. And again, we need to have explicit integration at the moment because it is advantaging because of the single instruction multiple thread. But there is the plan, of course, to introduce in the future other, let's say, ODE integrators, and that could be done exactly as it is done currently in OpenFOAM. So you can select which kind of ODE integration you want to use on the GPU. So let's move to the numerical solvers. Thanks to the fact that OpenFOAM is object-oriented, okay, let's say we have this advantage because whenever you compile this new GPU ODE integration, you can combine it with the solvers which are already available in OpenFOAM that, of course, take into account the presence of finite-rate chemistry. So what you have as the simplest solver is, of course, ChemFOAM. So I am talking about, of course, single-cell batch reactors. But you might have something which is, of course, taking into account also the fluid dynamics. So, for example, reacting foam, or in some sense, you can develop your own solver. So, for example, you can extend raw central foam to take into account, for example, density-based shock capturing solver, which also includes possibly the presence of the finite rate chemistry. Okay, and in all these solvers, finite rate chemistry is handled in the same way. So the GPU-ODE integration was designed in one single way. And of course, it can be used on the different solvers that you have. Okay. So upon its compilation, you can use it on whichever solver. We decided to start by using single cell batch reactors for one particular reason. As I said, what we get with the GPU is the reaction rate, which of course on the GPU could be modified by means of combustion models, but at the same time to validate actually that the result that we get by means of this kind of operation on the GPU, we wanted to avoid any possible influence from external factors. So we wanted to remove the presence of fluid dynamics, and we wanted to remove the presence of, let's say, tuning of combustion models. So what we used was exaFOAM and studied the evolution, so just the ODE integrations. Of course, what we did was to study that by considering different fuels. So for example, here you see, say, what happens considering hydrogen reaction, ethylene reaction, or methane reaction, okay? And you also see what are the errors which are produced by means of this hybrid approach. So the solver is resident on the CPU, but it relies for ODE integration onto the GPU. And you see that they produce some slightly different results. Now, this is, of course, enhanced, let's say, because we used small tolerances, okay? You know that the results produced by means of, say, the ODE solution are affected by the kind of ODE integrator that you use. In this case, we used Runge-Kutta-Kashkarp both for the CPU and the GPU. But, of course, it's also dependent by the tolerances that you use. So you see some differences here, and this is quite common also in the literature, because you have that the GPU does not perform exactly the same operation as the CPU. The reason is that in GPU you have parallel operations, while instead on the CPU you have serialized operations, but it's also related to the architecture itself. So the register dimensions and the way that the information is stored, etc., and so round off or other numerical, let's say, discrepancies, they make the result be a little bit different. But don't be scared about that, because if you reduce the tolerances, or if you study your problem by considering, of course, the same approach, so the same settings, but a little bit more stringent, let's say, what you can have for, in this case, different thermochemical conditions is a solution which perfectly mimics, I would say, the result obtained by means of the pure CPU legacy code. So we compared here Cantera, used as reference, okay? And of course, we modified, let's say we created the script in Cantera to perform the operation at constant pressure, exactly as OpenFOAM is doing in its calculations. And then we compared implicit CPU, explicit CPU, and then, of course, we added the explicit CPU and GPUs. Again, this means solver resident on the CPU and ODE integration performed on the GPU. Now, of course, whenever you have single cell batch reactor, this kind of methodology, so the structure that we have designed, is not actually the most efficient one. Why is that? Because, as I said, the dynamic data needs to be continuously moved from the CPU to the GPU and backwards from the GPU to the CPU. This is something that you wouldn't want in exaFOAM, because you are only solving the ODEs, so there is no sense to actually move this information back to the CPU. So what you might want to do is to simply start from the initial condition, perform the overall integration, and then bring back this solution to the CPU, but while storing the intermediate solution, so the solution for different intermediate time steps, on the GPU. And once you transfer everything back, you can generate the same plots that you have here. The issue is that this does not work for multi-cell cases, because in multi-cell cases, you have influences by the other equations that you have. So you need to continuously, every single time step, move this information from the CPU to the GPU and backwards. And that's why, of course, another thing is that we have designed this by considering a double parallelization. This double parallelization considers the fact that you are solving concurrently multiple cells all together on the GPU. And so if you only have one single cell, you are reducing, let's say, the parallelization that you have on the GPU, of course. But this is instead extremely advantaging when you're handling some problems related, of course, to multi-cell cases Okay, so then once we had verified the correct result produced by the single cell batch reactors, we moved to let's say micro benchmark, okay, which are multi-cell cases. Multi-cell cases which are extremely popular, they are available in the literature, but also multi-cell cases that allowed us to consider, for example, laminar combustion. So they, or laminar turbulence models, for example, allowing us to still treat and let's say investigate what would have happened by considering multi-cell cases, but without introducing the presence of other external factors that could, let's say, have an influence on the final result for our simulation. For exception, of course, of fluid dynamics, which is present in this case. So as you can see, again, the result turns out to be really, really interesting. Okay, so the solution seems to be quite accurate. And in terms of performances, I want to state the fact that with respect to the test cases that we have tested up to now, in order for the GPU to be advantaging in solving the ODE equations, you need to have the time taken by the GPU, which is the summation of 4 times, must be smaller than the time taken to perform the same task by the CPU. Why am I saying that there are 4 times that need to be combined together? Because in CPU, you don't need to, let's say, manipulate the data, allocate the memory, and copy the data forward and backward from the CPU to the GPU, because you are only relying on the CPU. Okay? Whenever you instead rely on the GPU, you need to add to the overall calculation to investigate what the performance is, the time taken to allocate the memory, to copy the data from the CPU to the GPU, and vice versa. That's why you may, and then of course the time taken to perform the actual ODE integration. So the thing is that our performance is extremely advantaging in terms of ODE integration, because we are performing this with 2-level parallelization, but the performances have a certain drawback, which is not that, let's say, marginal, because of the presence of forward data copy, backward data copy, and data manipulation before these actual movement of the data among the different memories. The thing is that even considering the simple, let's say, cases that we have investigated in the previous slide, you already have some very good results. So what you have is that overall, so considering the 4 time steps, you have for simple test cases, so for example 1D problems, that the speed up is in the order of 2 pair, okay? So GPU plus the CPU against the same, let's say, configuration of the CPU. Whenever you make your problem more complex, you can get up to a speed up that can reach the order of 10 pair, okay? Overall, so we are talking about the entire simulation. The problem is, okay, that whenever you are going towards HPCs, and so massive parallelization, there is the need to have a greater number of GPU cards, which they are in principle seen as a whole, okay, but we still need to extensively validate what happens, and we are currently doing that, what happens whenever we go to a number of cores, which is much larger than the 128 cores that we have tested for this kind of configurations, okay? This is also because of the fact that we had small, let's say, test cases, and so there was no reason for us to go to much larger number of cores at the moment. But we are currently testing industrial test cases, and so this moves us to the analysis of what happens in much larger, let's say, configurations with much larger number of cores. So again, the tests that we are currently investigating right now, and I will not stay too much on this, are the jet inert co-flow JHC burner, whose geometry is provided by DLR, and these, let's say, benchmark is already published, so it's available for you to be seen. And we have already, let's say, launched our case in full CPU form while we were developing this methodology, okay? And we are currently doing the tests for massive number of cores combined to the GPUs for these particular tests. And the other test that we're currently investigating is the flux gas turbine that you have seen in the previous presentation as well. And so we are investigating this. Again, the geometry is provided by DLR in the two different configurations that we have, because there are two configurations available. One is the unpiloted configuration. The other one is the piloted configuration, for which the pilot inlets are activated. And that is, let's say, the major difference among the two different cases. And again, these have already been investigated by means of GPU, and we are now currently investigating this by means of the GPU as well, combined to the massive number, of course, of the CPU. So let me do some conclusions related to this, and then I will move to the extra that I was discussing at the very beginning. One thing that I want to state is that whenever you are dealing with GPGPU computing, you need to, let's say, produce some algorithmic co-design or redesign of the solvers that you have. Whether the, let's say, redesign is marginal or less marginal, it depends on the kind of operation that you're actually moving to the GPU. This is typically related to the fact that whenever you're dealing with heterogeneous architecture, and in particular with GPU computing, you need to exploit the architecture of the GPU. And in this sense, we did it by providing to you a methodology that allows to have a multi-level parallelization. Okay. Overall, what you have is a multi-level parallelization on different hardwares, because you are decomposing via MPI on the CPU, and then you are also exploiting the architecture of the GPU for a double decomposition on the GPU. And as I said, it's a fat thread approach. So I've already explained to you what it does mean in terms of memory management and ordering of the data. And as I stated, the cells are solved in parallel, relying on CUDA blocks, and the species are solved in parallel as well, relying on the CUDA threads. We, at the current state, have a good level of accuracy, as you have seen, and we have some sensible speed ups, okay, which is, of course, case dependent, because we have seen that whenever we increase the complexity of the chain, the speed up tend to increase. Whenever we increase the number of reactive cells inside of the domain, the speed up increases as well, because of the double parallelization. And we are currently, let's say, investigating these to derive some performances globally, even on industrial test cases. And the thing is that we want in the future to combine this kind of acceleration, so the acceleration produced by means of GPU odd integrators, with possibly other integrations, so other, let's say, solutions performed on the GPU, to have an improvement of the speed up overall. So moving to the extra, still related to the presence of heat transfer inside of your domain. The thing is that you can use the GPU also to accelerate, for example, the calculation of the view factors. And this is much simpler than the calculations of the ODE equations, because, of course, the calculation of the view factors relies on a ray tracing operation, which is done prior. So what we did was to implement two global functions. One is that which produces the calculation of the ray tracing on GPU. The other one is that which actually computes the view factors. And this is extremely important, because whenever you're dealing with heat exchange, in some industrial cases, we have experience of the presence of thermal radiation, okay? And so, of course, in most industrial test cases, what you have is a pre-processing that it's, in some cases, extremely long to be performed. So we wanted to accelerate that as well, okay? And in terms of memory and, let's say, management of memory and resources, The two global functions, in this case, they rely on the thin thread approach, but we still use the same concepts that we have, let's say, developed for the OD integration. So no race conditioning, branchless code, and coalesced data access. Because, of course, now that we are progressively trying to move portions of the codes onto the use, onto its development, let's say it's run on the GPU, we are, of course, learning from what we have done prior to, let's say, fasten up and improve also the development for the future applications. The procedure is extremely simple. You just, as I explained before, collect the data, you move the data to the GPU, you perform the two, in this case, operations. One is the ray tracing by using the same intersection algorithm, which is available in OpenFOAM. Then you perform the calculation of the view factors in parallel. Okay, so we're handling the rays in parallel for the ray tracing. We are handling the calculation of the view factors in parallel for the second global function. And then what we do is we retrieve the information. And of course, this allows us to solve, let's say, our problem, which is the calculation of the view factors, which is necessary for, let's say, the heat transfer because of radiation. The test cases that we have initially done they go from a very, very simple test, so this kind of annular 2D, to something which is a little bit more complex, and we are further complicating this by using now moving towards industrial test cases. And as you can see, the accuracy that we get by means of the calculation via the GPU is, let's say, very, very good in terms of CPU, so legacy CPU results, which also at high number of phases, let's say, tend to the analytical solution for the simple cases that we tested. We started from simple cases, of course, because we had the possibility to consider also analytical results, and of course this helped us a lot in validating, let's say, our approach. In terms of performances, what we have is, again, the fact that the sole ray tracing, for example, application is 12 times faster than the same operation performed on the CPU. The issue that we have in the current state is the fact that you need to manipulate the data before the actual transfer of the data from the CPU to the GPU. But even though we have this kind of drawbacks because of data manipulation and data copy, we still have a 2-pair speed up for the tests that we have conducted up to now. So overall, we have for the different tests global 2-pair speed up, but we want, of course, and this is what we are also currently doing, investigate the performances when we go to something which is industrial, as I said. So thank you very much for your patience and for your attention. I know that there are not so many minutes still available, but if you have questions, you can contact me via the email, or you can, of course, ask here, and I will try to answer them in the best way I can.
Thank you, Federico, for a very nice presentation. Then we are open for questions or any remarks that you have.